So there is an emitter plate, that is C, cathode, and there is collector plate, that is A, anode. So intensity means more electrons are emitted, hence more photocurrent is produced. So they are directly proportional to each other. The minimum value of negative potential at which photocurrent becomes zero, that is known as stopping potential. So the mass of the object is coming in the denominator, which means if an elephant moves, the matter wave will be very small. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence. And we are going to continue our chapter, that is dual nature of radiation and matter. The small experimental chapter holds a lot in its place, so let's see what it holds for us today. So again, in the previous session, we were discussing about what photocurrent was and how it was produced. Now, we are going to see what are the factors that influences this particular photocurrent. So there is an emitter plate, that is C, cathode, and there is a collector plate, that is A, anode, and both of them are connected towards battery so that they maintain opposite potentials. Now again, electron is accelerated in between producing photocurrent. All this we saw in the previous session. Now, if I increase the intensity of the radiation that is being driven into this particular emitter plate, what will happen to the photocurrent? That is what we are going to see today. That is effect of intensity on the photocurrent. That is, imagine that instead of one ray that is being incidenting on this particular metal surface, I send 100. That is, I am increasing the intensity. Keep in note that we are not increasing the frequency. We are not changing the kinetic energy, or we are not doing anything else. We are just increasing the intensity of the beam. That is, instead of a weak beam, we are sending a higher concentrated beam. That is, more intense beam we are sending. So instead of one ray, let me increase the intensity like this. Now I have increased the intensity. What will happen to the photocurrent? It's very obvious, right? When I increase the intensity, more electrons are being produced. That is, if one ray hits the metal surface, one electron is released. If more number of rays are hitting the metal surface, more electrons are produced or released or emitted, and they will be accelerated. Hence, we can say that with increase in intensity, the photocurrent also increases, which means that the relation between photocurrent and intensity is they are directly proportional to each other. That is, if intensity increases, photocurrent also increases. So they are directly proportional to each other. So again, just remember it like this. Photocurrent means that more number of electrons are produced, hence more will be the current. So intensity means more electrons are emitted, hence more photocurrent is produced. So they are directly proportional to each other. So there is a new term here in this place, that is stopping potential. So what is the stopping potential? So basically it's just what the name suggests. It is the potential that is applied in order to prevent the photocurrent from taking place. That is, in order to prevent photocurrent flow, the potential we apply or the negative potential we apply is known as stopping potential. That is, you remember the experiment, the electrons are passing through the circuit. So we apply a potential in the opposite direction or in the negative sense so that the entire photocurrent flow in that particular circuit is stopped. So we can imagine it in this way, that is, if I increase the potential, if I am increasing the potential, then automatically electrons are accelerated more. That is, V is directly proportional to I, which means that if I increase the potential, automatically the photocurrent will also increase. So, which means that the photocurrent will increase up to a point and it will saturate. So this particular point where the current can increase to a maximum value, after that even if I increase the potential, the current will stay at that particular level itself. So that particular level, that is this particular level, is known as saturation point. That is, beyond that you cannot increase and expect a higher output. You cannot increase the potential and expect a higher output because already the peak value has been reached. So if you increase the potential, it will reach a peak value and that is known as saturation point. Beyond that, you cannot get any output. So again, the point here is that about stopping potential. So stopping potential means that I am applying a potential in the opposite direction, which means that I am trying to stop this particular current flow, which in turn means, okay, this I am applying the stopping potential, which means it is in the opposite direction, which means it is negative. So that I am applying a negative potential, slowly the current will decrease and slowly the entire photocurrent will stop at this particular point. So you can actually define stopping potential as the minimum value of negative potential at which photocurrent becomes zero. That is known as stopping potential. So mathematically, we can also derive a relation from this. That is, we know that the kinetic energy, let's say the final kinetic energy of this particular system, KEF. So KE subscript F. So the final kinetic energy of this particular system will be equal to 0, right? That is, kinetic energy will be maximum when current is flowing through it. Now we are slowly stopping that particular current, which means we are preventing the electrons having higher kinetic energy. We are putting that motion to rest. So that means that the final kinetic energy will be 0 and the initial kinetic energy will be maximum, right? So the initial kinetic energy will be maximum and the minimum kinetic energy or the final kinetic energy will be 0 only. And you have already learned in your first PUC, that is work energy theorem, states that W, that is work done, is equal to change in kinetic energy, or simply here we are taking the magnitude value. So I can simply take Ki minus Kf, right? Initial kinetic energy minus final kinetic energy will give you change in kinetic energy, magnitude of that value, and that will be equal to the work done in that particular circuit. So again, what is work done? The work done here is that we are accelerating a charged particle between two metal plates. So a charged particle, that is Q, is being accelerated between a potential difference. So QV is the work done here. Again, you can imagine it as QV, or more precisely you can say that, okay, this Q is actually an electron, so you can say that it is EV. You don't need to put the negative sign in because we are considering the magnitude value. So again, EV is equal to Ki, which is maximum kinetic energy minus 0. So EV is equal to Ke max. That is what the equation will arrive at. So again, this is the final form of the equation we will arrive at. But if you want to do it in the other way also, that is final minus initial, that is also fine. The only difference is that then you have to take the electron as negative. So negative and negative will cancel each other out, and finally you will get EV is equal to Ke max, or EV naught is equal to Ke max. Both are perfectly fine equations for stopping potential. So again, we learned about what stopping potential is. Now we are going to learn about what is its effect on the photocurrent. So again, you know that when the incident frequency, that is when the incidenting radiation has a higher frequency, the energy is automatically higher, which means that the kinetic energy imparted to the electron will also be higher. So we can just say that greater the frequency of incident radiation, greater will be the kinetic energy of the photocurrent, which means that the electrons in that particular system will have more energy. Now, if the electrons are running around with more energy, then a higher stopping potential will be required in order to stop those particular electrons. So that is the relation between stopping potential and photocurrent. That is, if the incident radiation has high frequency, then automatically stopping potential also will be very high. If it has low frequency, then stopping potential required will also be very low. That is just the effect of stopping potential. Now again, what is the effect of frequency on this particular stopping potential and photocurrent? So again, you know that stopping potential actually affects what is the photocurrent, because higher the frequency, higher the stopping potential. We already saw that. But again, how is it affecting? So if you plot a graph between, that is, frequency of the incident radiation against stopping potential, you'll actually see that experimentally also it is directly proportional. Just before we learned how theoretically it is proportional, so experimentally also you'll get the exact same value. Now, why the graph is not plotted here and after some distance like this is because, again, for photoelectric effect to occur, that is, for photoelectric effect to take place, there should be a minimum value for frequency that is known as threshold frequency. So from the point of threshold frequency, now we are getting the frequency directly being proportional to stopping potential. So you can just say that, okay, frequency is directly proportional to stopping potential. Frequency is directly proportional to stopping potential. This is the experimental proof for that, and this is the graphical representation. Now again, just like we did in the case of intensity, I'm going to increase the number of frequencies of the wave. That is, instead of giving one frequency to the emitter plate, I'm going to give multiple frequencies. So how does that particular affect the photocurrent? That is, how does that particular change affect the photocurrent? If I increase the number of frequencies of the waves incidenting the metal surface, what will happen to the photocurrent? So again, at the saturation point, it will be same only. As we do the stopping potential, as we apply the stopping potential, then only the effect of frequency comes into play. Again, this is against photocurrent versus potential. So when we apply the stopping potential, then we see that stopping potential is directly proportional to frequency, which means each of the frequencies will have independent or different stopping potentials. So that is indicated here. For a mu1, that is, for a wave of frequency 1, it will have stopping potential V01. For mu2, it will be V02, and similarly for mu3, it will be V03. Given that mu3 is greater than mu2 greater than mu1, this will be the effect of frequency on the photocurrent. Again, it's the same thing, just experimentally proven. So again, the last thing you need to know about photoelectric effect is that the laws of photoelectric effect, or simply the conclusion towards the experiment that was done here. So again, the only thing you need to remember is that saturation photocurrent is directly proportional to the intensity of the radiation. That is, again, you know that when more intense light is coming, more electrons are produced, more photocurrent is being produced. So that particular saturation value is directly proportional to the intensity of the beam and not on the frequency. And the next thing is that stopping potential is independent of intensity. If you increase the intensity or decrease the intensity, there is no change, because again, the frequency is the factor, that is energy given to that particular electron is h mu. So frequency is the factor that controls how fast the electrons are going. So obviously intensity just produces more of that particular electrons and not more higher energy stated electrons. No, the electrons that is produced won't have higher energies. They will have the same energy, but the number of electrons produced will be more. That's it. But the frequency is actually the factor that determines stopping potential. So below mu naught, no emission will take place. That is known as the threshold frequency. And above mu naught, that is above threshold frequency, stopping potential is directly proportional to the frequency. Again, we know that E is equal to h mu, and that particular h mu, that is the frequency, is the factor that determines how much energy is given to the electron, which in turn is converted as work function, which is used to escape the metal surface, and then the remaining part is used to gain the kinetic energy for the electron. And finally, photoelectric effect is an instantaneous process without any time delay or time lag. That is, if one ray of light comes like this, it is not like one ray of light hits after, let's say, 3 or 4 microseconds and then one electron is ejected. It is not like that. As soon as the ray of light hits, instantly the electron is emitted. So it is without any time lag. So this is the conclusion of the experiments, and this is also known as the laws of photoelectric effect. Now, the last topic in this particular chapter, that is de Broglie's hypothesis. So who is de Broglie? De Broglie is actually, even though it is spelled de Broglie, he is a French scientist, Louis de Broglie, and yeah, he actually predicted a few things regarding photoelectric effect. Like, from the experimental conclusions, he actually said a few things. But before that, what is the relevance of photoelectric effect? So, the famous argument, what is light? So again, Newton said that, okay, light is a particle. It is a corpuscular theory of light. It is the corpuscular theory of light. They're saying that, okay, light is a particle. But then Huygens said that, okay, light is a wave, and he absolutely proved that with the double slit experiment. But then Einstein came again with his photoelectric equation and said that light is nothing but wave packets, or simply quantas, which again, photoelectric proves that light has particle nature. So what exactly is light? Is light a particle or is light a wave? One of life's biggest mysteries. Is light particle or wave? Well, science says that they are both. Because depending on the experiment you are doing, light actually assumes the role of a particle or the role of a wave. It depends on what kind of experiment you are doing, what kind of procedure you are doing. Depending on that, light will actually act as a particle as well as a wave. That is very interesting. So again, when light is acting as a wave, we can explain the process of interference, diffraction, polarization, and so on. There is no problem. But if we assume the same wave nature, certain other effects cannot be explained, such as photoelectric effect, which we just saw, proves the particle nature of light. So we have to assume light as a particle in order for that effect to take place. And the second effect is Compton effect. Compton effect is another effect. Compton effect just means that When light ray of higher frequencies like X-ray or gamma ray is projected towards loosely bound electrons, just like in the metal surface, it scatters that electron with the emission of another photon, that is known as Compton effect. Again, you don't have to study the theory of that, but in order to explain Compton effect also, you need particle nature of light. And finally, the ultraviolet catastrophe in the physics world, that is known as black body radiation. Black body radiation. Again, you don't need to know what black body radiation, Compton effect, and all these other phenomena are, but these are experiments, or these are situations where if light is not considered as a particle, you won't get the mathematical output we are used to getting. This actually proves that light actually behaves in two separate different identities. It is the same light that we are using, but in different cases, we are getting different outputs. This particular dual nature of light is what puzzles scientists. So again, depending on the experiment you're doing, light assumes the role of a particle or a wave. So again, using this particular analysis, de Broglie actually assumed that if you're considering photon to be a particle, then other subatomic particles such as electrons, positrons, neutrons, etc. will also have a tendency to behave like particles. Again, Einstein only hypothesized that, okay, this particular behavior, that is a ray of light, meaning photons are actually very small packets of energy. So de Broglie actually hypothesized that, okay, if that is true, then this should be true for other subatomic particles also, that is electrons, protons, neutrons, etc. Which means that higher states of matter also should follow this particular rule. That is, they should also be wavy in nature. So again, what de Broglie hypothesized was that, okay, particles like electrons, protons and neutrons should also have this particular wave nature when they are in motion. Because again, photons have this particular behavior, that is, light has this particular behavior, that is, when it is moving, it is always in motion. Photons do not really have what is known as a rest mass, they only have relativistic mass. They are always in motion. So again, de Broglie hypothesized that, okay, when things are in motion, when matter is actually in motion, it should also produce waves. That is also applicable to us because we are also made up of electrons, protons, neutrons and everything. So when we are also moving, we actually produce this particular waves. But this is not detectable to anyone because it is actually related in this particular sense. That is, the wavelength that is being produced, that is known as de Broglie waves or matter waves. So these particular waves are known as de Broglie waves or matter waves, and this particular wave is detected or found out using the equation lambda is equal to h by p, where h is the Planck constant, that is 6.624 into 10 to the power minus 34. So again, that will be equal to h by p, which is equal to h by mv, where p is the momentum, so it is mv. So the mass of the object is coming in the denominator, which means if an elephant moves, the matter wave will be very small. But if an electron moves, the matter wave will be very, 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 very large. That is why we can detect matter waves for electrons, but is very hard to detect the matter wave for an elephant or a blue whale for that matters, because here the mass term is coming in the denominator, hence the wavelength will be very small as you get massive and massive. So that is all about de Broglie's hypothesis, and with that we are finishing up the 11th chapter, that is dual nature of matter and radiation. So I hope you have understood everything in this particular chapter. I'll see you all with a new chapter. Until then, thank you.